Hello. The topic of my presentation is quantifying the change in landslide hazard as a response to weather fluctuation and climate change. As all of us know, landslides are one of the most interesting yet unknown phenomena in geotechnical engineering. Landslides happen everywhere, and thus knowing their behavior can help us minimize their destructive effects. According to Natural Resources Canada, landslides account for an estimated $200 to $400 million in direct and indirect costs annually. In Alberta, many vital infrastructures have been constructed close to unstable slopes that are prone to failure. CP has reported that they have lost $75 million between 1960 and 1995 as a result of rock falls, earth slides, subgrade failures, and erosion events. This is more than $2 million per year. Therefore, it's important to understand the nature of landslides and parameters that affect their behavior. One of the parameters that cause a landslide to happen are weather-related parameters, such as precipitations, freeze and thaw cycles, weathering, and air temperature. Better understanding of the effects of weather-related parameters on landslides is the main idea behind my research. Many researchers have studied the effect of climate variables on landslides and tried to find the relationship between them. However, there are key questions and notions that are still not discussed in the literature, and it seems that this problem is still insufficiently explored. For this reason, in this research, a comprehensive study will be conducted in order to address these questions. 1. What can we expect from landslide intensity in light of a changing climate, and how is this translated into changes in risk posed to railway operations? 2. Can we provide weather-based quantification that will allow us to build warnings but also quantify the effects of climate change and landslide hazard? We have defined a number of objectives for our research. Our major objectives in this research are to develop a methodology to quantify the change in regional landslide risk due to climate change. This methodology will be applied for a region in Alberta with focus on deep compound and translational landslides in the prairies. Another objective is to develop a method to quantify the change in landslide risk at a local scale with limited failure data and as a response to weather. We also want to develop an effective warning system at the local scale, and also to develop a decision tree that results in a failure probability by considering the geology, geometry, and weather information of the desired locations. My research consists of two parts. In the first part, I want to evaluate landslide risk change with climate change in a regional scale. As I said, the main objective of this part of my research is to develop a methodology to quantify the change in risk associated with landslides due to climate change. To do so, landslide incidences on the Battle, Red Deer, and Bow rivers will be mapped in the Bear Paw Formation in southern Alberta, and the landslide activity along each river will be investigated. The extents of the Bear Paw Formation in Alberta and the locations of Battle, Red Deer, and Bow rivers are shown in this figure. The study areas are shown with a red borderline. In this study, I used several available resources, some of which are raw weather information of the last 80 years that will be extracted from weather organizations of Alberta and Canada. I will also use LiDAR data, remote instruments, aerial images, UAV images, point cloud analysis, and general computing software. ArcGIS is the main software I use for my analysis at this point. You can see LiDAR data for Battle River, Red Deer River, and Bow River. LiDAR data are one of the most useful resources that can be used to locate the past landslides along river valleys. In my research, I used LiDAR data and ArcGIS built-in imagery to delineate landslides along these three rivers. The resolution of the LiDAR data for my research is 15 meters. In these figures, you can see the landslides that I found along the rivers. Using the LiDAR data, I can determine the dimensions, slope angle, and azimuth of each landslide, which helped me build a database and perform a statistical analysis. To have a better vision of the future weather conditions, I have plotted the mean seasonal temperature and precipitations for the next 60 years at a location in the study area using the Global Climate Model Axis 1-RCP 4.5. As you can see in the left figure, the average temperature increases in all seasons with an average of 4 degrees over the next 60 years. On the other side, in the right figure, it seems that the average precipitations do not change significantly with time. However, an increase of about 20 mm is expected in springs. Once the relationship between failures and weather triggers is known, we can use climate models to have an idea of the possible number of failures in the future. I've brought this figure to show a comparison between the mean annual precipitation from 2013 to 2050. This kind of data, these rasters, can be used to find the qualitative relationship between weather and landslides. Climate models show an increase of about 10% in mean annual precipitation across Alberta in the next 30 years. This is a short video showing the locations of the study areas. This is the hillshade I've created in ArcGIS from the LiDAR data for the Red Deer River. The elevation scale has been enlarged to give a better vision on the river valleys. The length of the selected section of the Red Deer River is about 140 kilometers. The location of the CN track relative to the study area is shown here in red color. The railway passes along the Red Deer River from Rosedale to north of Drumheller, and just about 10 kilometers northwest of Drumheller we have another study site along the road number 837 called CO18. This is a 3D model of the site made using the photos taken by a drone. This slope is located adjacent to the highway and has a history of erosion on the riverbank slopes, rock falls, and soil slides. Since 2000, 10 landslides have been recorded in this area. Some signs of sliding are visible in the model. The CO18 research site that was shown in the video consists of a 500 meter long, 60 meter high rock slope and is located on a weak, poorly indurated sedimentary rock with layers of stronger sandstone, siltstone, and coal. Preliminary studies showed that a relationship exists between rainfalls and landslides at CO18. Therefore, in this research, we decided to look further and investigate the effect of weather-related parameters such as precipitation, temperature, and freeze-thaw cycles on landslide at the CO18 site. Up to 2018, Alberta Transportation has reported 10 landslides happened at the site. And except one that happened in the winter of 2017, all other incidences have occurred during the springs and summers, or more precisely between May and July. According to published reports, soil slides, earth flow, and rockfall are 3 types of failures that have been identified for failures happened at this site. To perform the weather analysis, available monthly, daily, and hourly data were collected from 5 nearest weather stations to the study site. The locations and the time span of the weather stations which were used in my analysis are shown in the figure. Total annual precipitation and mean annual temperature have been plotted against time and the number of actual failures for the CO18 site. While average temperature hasn't changed too much in the past 20 years, the total precipitation has become almost double and increased from 200 millimeters in 2006 to about 400 millimeters in 2018 at the CO18 site. In another analysis, I calculated the cumulative precipitations at certain days before each failure to find the signature that causes these failures. And at the end, I selected one of these events, the May 2018 event, which is shown in the right figure as a triggering event. And I used the result of this event for my further analysis. So based on the May 2018 event, 3 probabilities were determined. First, the likelihood that a failure happens in the last 20 years if the criterion is exceeded, which is 7.3%. Second, I calculated the likelihood that a failure happens if the criterion is not exceeded, and the result is 0.03%. And third, the rate of days when the criterion was exceeded but no failure has happened, or the rate of false alarm was calculated. And the result is 92.7%. The main objective of this study should be maximizing the first number and minimizing the false alarm rate, which is possible by defining more criteria and expanding the available database simultaneously. These are some notes about the analysis that are being done on the CO18 research site. This analysis provides a crude estimate of expected results. We use probabilistic approach to quantify the effects of climate change on landslides. And because we have very limited landslide data for this site, the probabilistic approach is based on a set of weather conditions indicating periods with higher potential for landslide events and analysis on the failure mechanism at the site. In the next step of my work, I plan to use the binomial theorem to calculate the probabilities and will also use the Bayesian updating in the warning system. One of the objectives we have is to develop a warning system for this site. And as I said earlier, the number of recorded events at the CO18 site is very limited, so using the Bayesian updating method, we can always add the new events to our calculations, update the probabilities, and update the warning system accordingly. I've summarized my presentation into 5 main points. For the CO18 project, preliminary studies showed that climate, especially the precipitation, has direct and indirect effects on landslides at the CO18 site. Separate analyses were done on precipitations to calculate the likelihood of an event at the site, and different criteria were defined based on precipitations, and the dates that seemed to be more prone to failure were determined. And for the second part of my research for the regional study, I used LiDAR data and aerial images to locate the landslides and their characteristics along Battle, Red Deer, and Bow rivers. And the future weather maps were extracted from available climate models. In the future, I will continue reviewing the literature to stay up to date, and I will try to define more criteria for the weather analysis, and the corresponding dates at which a landslide is possible will be determined. I will implement neural networks and machine learning techniques in landslide susceptibility analysis, and I will continue updating the landslide inventory of the region. This is the last slide of my presentation. Thank you for listening, and please let me know if you have any questions.